Okay, g'day all and welcome to another video. So today what I wanted to do is continue exploring the x86/x64 instruction set in assembly language, and what we're going to look at today is the basic floating point arithmetic instructions. So we're going to look at 4 operations today. They're just your basic arithmetic operations: addition, subtraction, multiplication and division. We're going to look at both single precision or 32-bit floats and double precision or 64-bit floats. We're going to be looking at the SSE versions of these instructions, but we're also going to look at the AVX versions of the instructions too. So there is another more modern instruction set called AVX 512, but at the moment that's not supported by AMD CPUs, and it's actually got a whole bunch more functionality. So we might leave that AVX 512 instruction set for a different video. So I've written a companion ebook for this video that I'll be putting up for the Patreons, just as a big thank you for supporting the channel. And if you'd like to support the channel on Patreon, I'll put a link up above and another one down below. Cheers. Okay, so just as a recap before we dive into SSE instructions, the SSE instruction set actually has vectors of 128 bits wide. So there's 16 different registers and they're called XMM0 all the way up to XMM15. And one of the things that I wanted to cover today was intrinsics as well, because I think a lot of folks might find that more convenient for their project. Yeah, so you don't have to code in assembly if you don't want. So today we're going to be looking at not only the assembly instructions, but also the intrinsics. Okay, so if we just have a bit of a look at the add PS instruction, just an example code just here. This is the instruction just here, the instruction intrinsic for add PS. The data type that you use for SSE floating point instructions is __M128. And you've also got to include intrin.h at the top of your file if you hope to use intrinsics. All right, so right here I've just defined 2 little vectors. So if we're dealing with single precision, then they're 32 bits each. And so the SSE vectors can actually store 4 at once. And then down here, we've actually called the assembly instruction add PS, using the intrinsic with a rather catchy name _MM_add_PS. Okay, so what the instruction does is it adds corresponding elements. So it's going to add the corresponding elements of our 2 input vectors, V1 and V2, and then it's going to store the result in V3. So we're going to get 1 plus 5, 2 plus 6, 3 plus 7, and 4 plus 8. Okay, so what I might do is just run this and step through just so that we can see exactly what happens. Okay, so here's my watch window just here. I think it starts docked down the bottom here, but I kind of just float it because I'm feeling dangerous. Add a watch to this vector just here. Okay, so V3 is going to be our destination. You'll notice that the watch window kind of gives you all of the information at once. So there's a whole bunch of different ways of interpreting the data. For us, we're working with float 32 or 32-bit floats. So this M128_F32 is the data that we're looking for. And we can see at the moment that there's nothing particular in there, it's just kind of random. But if we step over this little instruction just here, then we'll see that the vector V3 is updated and it now stores the result of summing each of those corresponding elements. So this element-wise operation is really where SIMD gets its name. We're providing one instruction just here, that's addition, and the operation is performed on multiple data. Yeah, so single instruction, multiple data, SIMD. Okay, so that's the C++ compiler intrinsic for adding packed singles. If you wanted to subtract packed singles, then all you've got to do is change the little intrinsic just here from MM_add_PS to MM_sub_PS, and then we're going to get an element-wise subtraction. So let's just have a bit of a run through that and see what happens. Okay, V3 down here. There we go. -4, -4, -4, -4. So that's the result of subtracting the second operand, or this V2 just here, from V1. Yeah, so 1 minus 5 gives you -4, 2 minus 6 gives you -4, etc., etc. Okay, so that's addition and subtraction. If you'd like to multiply, then it's pretty easy as well. The intrinsic just there for mul_PS is MM_mul_PS. Simple as that. Let's give this a run. 1 and 5, 2 and 6 gives you 12. 3 times 7 gives you 21, and 4 times 8 gives you 32. So multiplication is pretty easy as well. And finally, the 4th operation that we want to look at is div. So with the div instruction, you do have to be aware that it's the elements of the first operand, or this V1 just here, that are divided by the elements of the second. Yeah, so we end up with 0.2, 0.33, 0.43, and 0.5, which is 4 divided by 8. Okay, so each of the intrinsics actually corresponds to an assembly instruction. So MM_div PS just here corresponds to the SSE instruction div PS. And we can see that if we like, if we just put a little bit of a breakpoint right here on this instruction and we run it, you'll notice that I'm in debug mode. I don't want the compiler to optimize out what we're looking at here, but it might in production code. But what we need is our disassembly window. So when the program stops at a breakpoint, if you're looking for your disassembly window, you want to go up to debug and windows and come all the way down here to disassembly. Yeah, just there. All right, mine's already open at the moment. Okay, but if we have a look at this mess of disassembly just here, one of the things that we will see is the div PS instruction. Yeah, so the compiler intrinsic pretty much corresponds word for word to that instruction. Yeah, when you use intrinsics like this, you're causing the compiler to emit the assembly instruction. Okay, so that is the compiler intrinsics. Let's have a bit of a look at assembly. I'll just make a little function call here. I could have set this up beforehand. All right, so here is some assembly code to achieve much the same thing. So this first example just here, we're looking at the add packed singles instruction, and you'll see it just down here. vec1 defined at the top in the data segment. So that's just a little SSE array of 4 elements, the same as the C++. They're defined as real4, which is the assembly name for a floating point number. And then underneath that, I've defined another vector, vec2 with 5, 6, 7, and 8. I've moved the data from these RAM in the data segment over to registers XMM0 and XMM1. And I'm using the mov UPS instruction just here. Mov UPS just means move unaligned packed singles. So all these first 2 instructions are going to do is move these little arrays into the SSE registers XMM1 and XMM0, and then we call the instruction itself, add PS. It's going to add the corresponding elements between each of the 2 vectors just here, and it's going to store the result in the first operand. So SSE is actually called a destructive instruction set because it just destroys things. It destroys some of the input. Yeah, so it overwrites this first operand just here. Yeah. All right, but what we might do is just have a bit of a run. All right, V3 is undefined, you don't say. Adios. Alrighty, so we're going to add a watch here to the register XMM0. You'll see the watch window gives you much the same information as before. It displays the register as, you know, all of the data types together. But the one that we're looking at here is F32, so I'll just expand that. So at present, XMM0 just has the vec1 data that it read. So 1, 2, 3, 4. But if we step over this line, you'll see that the elements are added. So we get 1 plus 5 gives you 6. 2 plus 6 gives you 8, etc., etc. So if we look at the specification for the add PS instruction in SSE, you might notice that you can actually use a memory operand as the second operand. So we could do something like this if we wanted. That would be fine as well. So that's a good idea there if you're running under register pressure. If you're running out of registers, it's often a good idea to keep this sort of thing in mind. There is a bit of something that you've got to be careful of, and that's that for SSE, these memory operands, when used like this, they have to be aligned to 16 bytes. So the data segment itself is aligned to 16 bytes, and vec1 just here is 16 bytes wide. So in this example, vec2 will be aligned, but if we just run it, yeah, there we go. So the addition occurred perfectly fine then. But what I do want to point out is what happens if you try to add PS, the SSE instruction, without aligned data. Might just DD0, I guess. So if I add this extra D word just here to the data segment, then the address of vec2 will no longer be aligned. When we talk about data alignment, all we mean is that the address has to be evenly divisible by some number. Now, the address is not going to be evenly divisible by 16. This data is not aligned for a SSE vector, and we should run into a little problem. Hey, there we go. All right, access violation, reading location -1 of all things. Yeah, it's a little bit of a strange message, but that's all it's telling us. It's just telling us that the data alignment of this second operand was not 16 bytes. Yeah, so you can actually put up here in the data segment align 16 if you want, or you can use aligned malloc in C++, that sort of thing, to ensure that your data is aligned for SSE. Yeah, as we move over to AVX, we'll see that the restrictions on alignment have actually been relaxed. Okay, and just like with the intrinsics, if we'd like to perform the other operations, they're fairly simple as well. So if we want to subtract the elements of our two operands, we could use sub PS, just like this. And that's going to subtract the second operand from the values in the first. And once again, because SSE is destructive, it's going to overwrite the elements of the first operand. We can multiply with the mul PS instruction. That's just going to give us 1 times 5, 2 times 6, 3 times 7, and 4 times 8 in XMM0 just here. You can also divide if you want, div PS. So do keep in mind that the first operand is divided by the second when using div PS. Yeah, the order is important with division and subtraction. Okay, so before we switch over and start talking about double precision, I just want to quickly mention that there is scalar versions of all of these. So add SS is add scalar single, and sub SS is subtract scalar singles. So the scalar versions are the same as the packed versions or the PS versions. The only difference is that the scalar versions actually only operate on the lowest element of the vectors, and they leave the rest unchanged. Okay, so that's a little rundown of the original SSE floating point instructions. Let's shift over to the double precision floating point instructions. So we might start with add PD or add packed doubles. Few changes that we've got to make. First of all, it's going to be mov APD or move aligned packed doubles in this instance. So in SSE, the vectors are 128 bits wide, so they can operate or they can function on two 64-bit doubles at once. So we might just change our little vectors here. Okay, so once again, this is just going to do an element-wise addition. So these double precision floating point operations were actually added in SSE2. Yeah, so let's open up our little watch window again. The data type that we're looking at here for real 8 is going to be M128 F64 in our little watch window. So let's expand that. 1 plus 3 gives you 4 and 2 plus 4 gives you 6. Would you believe it? That's unbelievable. All right, so it's just done an element-wise double precision addition just there, add PD. If you'd like to subtract doubles, then it's not very difficult. You'll just use sub PD. We've also got mul PD, multiply packed doubles, and then of course we've also got div PD or packed division. Okay, so those are the assembly versions of the instructions. Just add PD, sub PD, mul PD, and div PD, nice and easy. Let's have a bit of a look at the intrinsics for the same thing. So the data type that you're looking for is __M128D, and they correspond to little vectors that can store two doubles. Once again, the intrinsic actually takes two operands. So right here we've got the add packed double intrinsic. That's just _MM_add_PD, and then we use a store unaligned packed double down here to store it in this little array and print out the values. So let's just have a bit of a step through and see what happens. So we should just get 4 and 6. And we'll add a watch to the V3. So you will see that the watch windows are a little bit nicer when we're using these double precision versions. Yeah, so the watch window actually knows that we're looking at double precision data here. But the elements that resulted from those two sums are 4 and 6 in V3. So the intrinsic for sub PD is pretty much what you'd expect. Yeah, just MM sub PD. Then we've got MM mul PD. If you wanted to multiply your elements, it's just going to give you 3 and 8. In your result, and then of course we've got div PD as well. Those are the intrinsics for the SSE2 double precision operations, add, sub, mul, and div. What we might do now is switch gears a little bit and talk about AVX, or the advanced vector extensions. So just as a little recap, the advanced vector extensions came about, I think it was 2011, and they actually deal with twice as much data. So the vectors in AVX are 256 bits wide as opposed to SSE's 128. And the AVX registers are named YMM0 all the way up to YMM15. It is important to keep in mind that the low 128 bits of the AVX registers is actually the SSE registers. So XMM0 is actually the low 128 bits of the YMM0 register, etc., etc. So these things are kind of all aliased together. Alright, but we do have to make a couple of changes to our project in order to get it to use an AVX intrinsic. So let's have a bit of a look at that before we jump over to assembly. So the vector data type for AVX using intrinsics is __M256. So 256-bit vectors can actually store 8 single precision floats at once. So I've just defined 2 little vectors up here, V1 and V2, and we've just put in 8 values in there. And down here we see the AVX intrinsic for V add PS. Really the only difference here is that we do have to put in a 256 just here into the intrinsic name, just so that the compiler can figure out that we want the AVX version and not the SSE. But all that's going to happen here, we're going to get 8 little sums, 8 little additions, 1 plus 9, 2 plus 10, 3 plus 11, etc. And then I've printed out the results. So let's just have a bit of a run and see what happens. V3, all right, what have you got, V3? Okay, so it has figured out that they're floating point in the watch window, which is quite nice. But V3 has the results of those sums. 10 is 1 plus 9, 2 plus 10 gives you 12, etc., etc., all the way down to 8 plus 16 gives you 24. You could do sub-packed singles if you want. That's just going to subtract the second operand from those of the first, and it's going to store the result. We've also got an intrinsic for mul-packed singles. It's just going to multiply all of the corresponding elements, and then of course we've also got an intrinsic for the div-packed singles instruction. So pretty basic stuff, really. Alright, so that is intrinsics for the AVX instructions. I'll just call it go ASM again. Let's have a bit of a look at how this stuff works in assembly once again. I keep deleting this, I don't know why. Okay, I don't know why that's underlined. It's just underlined for some reason. But anyway, this is just an example here of the same instructions using assembly, and we've got a couple of interesting things to point out. So for one thing, the vectors are 8 floats as opposed to 4 from SSE, like we just saw in the intrinsics. So we've got vec1, real 4, and then 8 little floats defined here. And we've got vec2, real 4, 8 little floats. And we're using vmov UPS as opposed to mov UPS. You've got your YMM registers instead of the XMM registers, and YMM PTR or YMM word pointers. So vmov UPS is just going to move vec1 into YMM0. This second vmov UPS down here is just going to move vec2 into YMM1. And then we have the vadd PS instruction itself, which is what actually performs the addition. Now you'll notice that it actually takes 3 operands now in AVX. So what this instruction actually does is adds the elements from the second and the third operands, and it stores the results in the first operand. So the first operand doesn't have to be one of the 2 inputs. So AVX is actually called a non-destructive instruction set, because when we perform an operation, it doesn't necessarily overwrite the inputs. Of course you could if you wanted to. You could just overwrite one of the inputs by using the input as the output, something like that. But let's just change back to YMM2. I'll hit save, I'll put a breakpoint there, and we'll run. We'll have a bit of a watch at YMM2 and see what happens. Okay, so at the moment YMM2 has nothing in it. I'll just expand the float 32 section so that we can see the floats. If we step over this instruction, you'll see that YMM2 gets all 8 of the results. So they're computed really, really fast. I mean, this instruction just executed in about half a clock cycle or something. Once again, in AVX, we can actually use a memory operand as the final parameter. Only the final parameter, mind you. And thankfully in AVX, the memory alignment requirements are relaxed. So this third operand doesn't actually have to be aligned anymore. But this will do exactly the same thing as before. It's just going to add these vectors together and store the result in YMM2. There we go. Okay, so the other functions in AVX are pretty simple as well. We've got v sub PS is going to subtract 8 packed singles. We've also got vmul ps, which is just going to multiply the corresponding elements. And then, of course, we've also got vdiv ps, which is going to divide this second operand just here by the values in the third and store the result in the first. So something else that the AVX instruction set added was the ability to do these functions in a non-destructive way to 128-bit SSE registers. So if you want, you can do div ps, something like that, and then supply SSE registers instead of AVX registers. You do need the V at the start. It is actually an AVX instruction. Yeah, it's not an SSE instruction, so you need the V at the start. But non-destructive 128-bit vectors as well as non-destructive 256-bit vectors. Okay, but let's just quickly switch over to double precision. Pretty much the same as before, except that the data type that they're going to be working on is a real 8 or a double precision, 64-bit double precision float. The AVX registers or vectors can store up to 4 values in double precision at once, and the instructions that you want are vmov upd for move unaligned packed doubles. If you do know that your data is aligned, you could do vmov apd, but we'll just stick to upd. So the instruction down here to add packed doubles is vaddpd. Yeah, and once again, it takes 3 operands. The second and third parameters are the inputs, and the output is this first operand just here. If we want, we can do vsubpd. That's just going to subtract. You can also multiply packed doubles if you want, mulpd. And of course you can div packed doubles, divpd. Okay, so finally, let's just have a bit of a look at the intrinsics for those instructions. So the data type for double precision AVX vectors in intrinsics is __M256D. Catchy name, and they store up to 4 doubles at once. So I've just defined V1, V2, and we're saving the result of this vaddpd instruction just here. So that's the intrinsic just there for vaddpd. Yeah. If you write an instruction, whether it's in intrinsics or if it's in assembly language, and the hardware is not capable of it, you actually get an illegal instruction crash. So let's have a bit of a look at that. Okay, so right here I've got some AVX 512 code. I've used intrinsics, but we could also call the vaddpd instruction and just supply ZMM registers. We'd get the same instruction in assembly. But if I try and run this, because this hardware just here is actually not capable of AVX 512, we'll get an illegal instruction crash. Let's do that, shall we? Look at that, unhandled exception at, and then it gives us a pretty amazing looking number, and it says SIMD arithmetic.exe, and then it says cooled and illegal instruction. Yeah, so you will get an illegal instruction error if you try to use intrinsics, or indeed the assembly instructions, and the hardware is not capable of it. So we've just looked at a whole lot of instructions. Just as a bit of a summary before we go, the mnemonics in assembly, they start with an optional V. So you use the V if you want to use the 256-bit non-destructive AVX instructions, or if you'd like to use the 128-bit non-destructive AVX instructions. After the optional V, we've got the operation that we're doing. So that could be add, sub, mul, or div. And after that, we follow it with either S or P, where the S means scalar and the P means packed. And the final part to the mnemonics is S or D, meaning single precision or double precision. Okay, and that's about all that I wanted to say. That's basic arithmetic instructions in AVX and SSE. There's a lot of different instructions, but they're all pretty basic, and they're really, really fast, so really worth exploring. There's a whole lot more instructions involved in these instruction sets too that perform a lot of different arithmetic, things like reciprocals and square roots, and reciprocals are square roots. There's fmad and all sorts of craziness. But we're going to have to leave that sort of thing for another adventure. For now, I just want to say thank you very much for watching, and I hope you have a really good day.